Just to let you know, I can't actually hear you. So if you're saying anything, your microphone is either muted or something like that.
Okay, can you hear me now?
Yes,
Hello?
we can. Thanks. Yes, we can hear you.
All right.
You're fine.
Are you watching my screen? Is my screen full now?
Yes, we can see a slide that says "Join us for the Dev Days of Summer," and it is your screen.
Oh,
so.
Perfect. All right. Thanks, Ian. All right. Hello. My presentation today is implementing try-finally code blocks in C++. My name is Miguel Angel Moreno. I'm an electronics engineer, and also I'm an IoT systems designer and architect. I also do software development and systems integration. I've been an Embarcadero MVP for more than 10 years now. So this is the agenda of what I'm going to present to you today. First, a quick history of the try-finally block, comparison with the try-catch, which is the standard sentence and structure that we know in C++. And introducing resource acquisition is initialization, which is what many of you might be thinking right now. What am I talking about? Why don't just use RAII? Then I'll show you some applicability of RAII by use case. And then a try-finally implementation for C++. An example of try-finally again by some of the use cases that I showed before for RAII. And finally, some questions and answers. All right, let's go ahead. And first, quick history of try-finally, which I find interesting to let you know. We associate try-catch, which is one of the key introductions of C++ compared to C, is exception handling. So we all think that it was C++, the big daddy of all these new structures to handle exceptions. This mechanism to handle flow structures is mainly two that we have. One is try-catch and the other is try-finally. But surprisingly enough, they were not introduced by C++. Lisp introduced the first genetic exception handling in the early 1960s. Genetic because it was not only for handling exceptions, but also almost any kind of error. But the programmer had a way to catch them. So by this combination of functions and keywords called error and error set, you would set an error code, and then the code would halt at that time and jump out. And then in the parent function, you could call error set to check whether that error flag was set or not. Then the programmer had a way to catch exceptions or catch genetic errors very, very early in the computing programming era, since 1960s by Lisp. Then MacLisp introduced dedicated keywords because the designers found out that error and error set were really generically meant to catch system errors, but they found out that the programmers were using this feature because they could catch the error without exiting the program. So that was a big feature. The error and error set could be custom handled by the programmer. When MacLisp came, which is a next generation of Lisp, the designer said, okay, we found out that that's very popular. Then they dedicated new keywords specifically for the programmers to throw logical errors and catch them at a higher level. Then it's MacLisp in 1972, the very first program that introduced throw and catch keywords for handling exceptions. Later, we have NIL, which is the new implementation of Lisp again, which introduced the first cleanup behavior that we know today as a try-finally block. It's only in NIL, in new implementation of Lisp, it's called unwind protect. But it works exactly as a try-finally. It's a piece of code that you can introduce that will be executed always, even when an exception is thrown. So you can have a way to do some cleanup behavior. So you can see that all of this was introduced by the Lisp family. None of this was by C++. But the concept was very popular by the time that Jan Sostrup created C++. So that's the reason he immediately introduced it into C++. Now, this is a quick comparison. Many of you will still be thinking why we want to implement try finally in C++. We already have try catch. Well, let me do a quick comparison. Bear with me for a second. Number one, this is how a try catch flow is when there is no exceptions. You have some external code, you enter the try portion of your try catch code with the code to execute. If nothing happens, there's no exceptions, everything goes fine, then the catch portion is simply skipped, jumped over, and then you continue with your external code outside of the try catch. That would be the normal process flow of a try catch. But when there is an exception, this is exactly what the try catch sentences were created for. When you have an exception within the code to execute inside your try code block, no matter where, can be at the very beginning, in the middle, or at the very end, but always inside your try code block, this structure will catch the exception and jump directly into the catch code block. So giving you the opportunity to catch and handle the exception properly. You can either handle it and then resolve it, or you could optionally throw an exception again, either the very same one that was launched in the try code, or launch a new exception of your own completely. So you are totally in control of what to do in the catch section. Now here, I'm assuming the normal flow, or the most common flow, which is you handle it and you don't throw an exception. That would be like normally the most normal code is you want to handle it yourself. Then the flow continues. Then the exception never terminates your program because you already handled it correctly. Now, this is what you are familiar with. This is the flows that you're expecting to see with a try catch flow. Now, try finally. Let's imagine for a moment that you had try finally in C++, but by the way, try finally is almost in any other language except very notably C++. But try finally behaves like this. You have, when there is no exception, you have the external code, you enter your try code block, the code to execute runs, assuming there's no exception, then it'll simply continue sequentially into the finally code block. Then you have some finalization or cleanup or whatever you want to call it, code block that runs after try. And then after that code, it jumps into the external code that you have, continues to flow normally. This is what happens when you have no exceptions within a try finally code block. But now when there is an exception, when it behaves similar but not the same to try catch. You go into the try code block. The exception can be thrown at any moment, either at the beginning, the middle, or the end of the try code block. Then the finally code is called immediately. So you have a chance to do some cleanup or finalization that you want to do. But bear in mind that finally doesn't handle the exception. It's only that it's allowing you, before it continues to call whatever handle you have to call the exception, to handle the exception, it allows you to do finalization or cleanup code. So finally is just like an interim process before continuing the throwing of the exception. So as you can see in this flow, after the finally code portion is called, where you do some cleanup or whatever allocation you need to resolve, then the normal flow continues. In this case, there's no handler, there's no try catch outside. Then the exception makes the program to halt or jump up to whatever exception handler may be, if there's any. If not, the program is terminated. Many programmers in languages that do have try finally are allowed to do a combination. Then you do a custom combination of try finally and try catch blocks at your will, depending on the logic that you are handling. Notably, we don't have this in C++. You would say, why do I need it? Well, let me show you. I'm introducing now RAII, which is resource acquisition is initialization. The creators of C++, John Sostrup and his team, truly believe that because of the feature of RAII, they didn't need to introduce try finally at all. They are mostly correct, but there are some corner use cases where you may want to actually have try finally. The interesting thing is that many other languages that were inspired by C++, notably Java, C#, and other out there, they do have try finally code blocks. It's only C++ that stays as the core mainstream language without implementing a try finally. Well, let me just compare what happens. I just show you this would be the normal flow with an exception of a try finally code. The idea in C++ is that to achieve sort of the same logic flow, you would do this. You would implement an object, which is what we call the RAII object, which is a temporary object. Temporary meaning is an object allocated on the stack that is the object that allocates or initializes resources. And that object, because it's a temporary one, stack allocated, it will automatically be destroyed at the end of the enclosing code block, which normally can be either a function or can be a forced code block, an indented code block made by you to force some, reduce the scope of the lifetime of the object. So we all, as C++ developers, know this trick, but bear in mind that this is the condition in order to use RAII. The core condition is that you are relying in the lifetime of an object that actually does the resource allocation and acquisition, and you are relying that the destructor of that object is the one that will actually deallocate or do the cleanup of that allocated resources. Then this is what you would do in order to achieve the similar flow of a try finally, but in C++ using RAII. Resource acquisition is initialization. As I said, RAII is excellent for allocating and deallocating resources needed only within the scope of a given function of code block. In other words, the scope boundaries are very delimited. It's either within a specific function or within a hand-coded code block. You are scoping it for the lifetime of the resources that you want to temporarily allocate. It is also called scope-based resource management because one of its main use cases is for declaring automatic variables. So those variables that we declare as automatic will be discarded and destroyed automatically at the end of their own scope. But this is the catch. RAII only works for resources acquired and released directly or indirectly by stack allocated objects. In this case, there is a well-defined static object lifetime. So RAII is notably not useful when we want to execute some finalization or cleanup code that is unrelated to the allocating resources. In other words, we want to run some cleanup code, but we are not necessarily bound to deallocating an object. Then how to run that custom cleanup code when we don't have an object that needs to be deallocated? So I'm going to show you some use cases and tell you whether they can be solved by using RAII or not. Number one case, again, this is not comprehensive. It's just out of my mind the very, very common use cases that you may be thinking or you are actually using and implementing in your code. So bear with me, I'll just show you some quick cases. The idea is to show where do I see a fit for a true try finally block. Number one, working with files. If you're using with standard C++ objects, then yes, you can use RAII here. You declare a myFile object of offstream, blah, blah, blah. You don't need to manually close the file. It will be closed automatically by RAII at the end of the record of add data record here. Use case number two, working with dynamic objects. Even dynamic objects is one of the very first cases that were completely covered by C++, especially after C++ 11, where there was a complete overhaul of the RAII objects that you can use for handling pointers. One of them is the one I'm showing here. We have the function process image. We are passing over a file name for an image. We need to create the object on the heap. Then we use a unique pointer, in this case, because no one else will be accessing it other than this function. So we create a unique pointer object that will actually manage and allocate the image object. Then we have the constructor, new image object with a file name, blah, blah, blah. We do some processing by applying some color filters and saving the file, but we don't need to deallocate it because unique pointer object will automatically discard and clean up the memory allocated for the image object. So again, this is another good case for using RAII. Working with mutexes, especially in parallel programming and multi-threaded programs, this is one of the best cases because there is always the risk that you forget to manually deallocate or unlock a mutex, and then you have a deadlock. So this is one of the most used cases for RAII when you need a temporary lock on a mutex. So again, you create the lock guard. This is one of the standard RAII objects introduced in C++11. So lock guard allows you to lock a mutex, and then you don't need to care once the function, in this case, write to queue, ends and finishes, it goes out of scope, then lock guard will unlock the mutex. And you don't need to worry about that. Even if there is an exception thrown when you are adding something to this queue, it doesn't matter. The compiler will unlock it because it's at the point of destructing the lock guard object that your mutex will be unlocked. So again, this is a good use case for RAII. And last but not least, we are executing finalization tasks after some database access. Look carefully at this code that I'm showing to you. We are validating new data record. So this is like similar, not exactly, but similar to the validate method that we have either in BCL or FireMonkey frameworks from Embarcadero for C++ in the RAD Studio developing tool. But anyhow, the logic is the same regardless. Is we already appended some data record in a database. There's has some fields, and then we call this function to validate whether the data in this record is valid or not. And if it's okay, then post the record, and then it gets permanently stored in the database. And you know the data records, when you have a data set objects, you could be in a temporarily edit state or append state. You need to actually confirm that this record is to be appended by, normally in the case of FireMonkey BCL, you need to call the method post, the function post, to have it permanently added to the database. So right now, when you call this function, you're in interim state, an interim edit state of the record, you need to validate. As you can see in line number 11 and 12, there's a simple validation made upon the data of this record field. And in case the age doesn't meet the constraint, then we throw an exception. So the problem here is that there's no way we are bounding the post process to a resource allocation. We are not bounding it to any RAII object that can handle it. So because of that, in case an exception is thrown, this data record is either not deleted or not posted. The state is undefined, which is not good, which means we are not clear whether it will be appended later or it will create some trouble for the next function that we call. This is not good. So this is one specific case where it would be nice to have a try finally code here. So even if I throw an exception, I can make sure that I'm finalizing whatever I need to do with a record in the database, either post it or cancel it, but make sure that I'm doing something to finalize that data record. So let me show you now a try finally implementation for C++. You would say, how is that possible? Well, it's simple. I'm using RAII itself to implement try finally. So I'm showing you here. This is a class called try finally. This class has a constructor. It has some internal flags. I'm storing two function data members that call two functions, one function called try, and another finally. Before I show you these internals, let me just call the program that shows you how this works. This is a test program implementing that class. The way I'm implementing it is by defining an object of that class. The object is called TF from the class try finally. Then I call try with a lambda, and the lambda is actually everything I want to do in the try section. So all this is the body of my lambda function that I'm assigning to try. After that, I call finally, the finally function, which again, its argument is another lambda, which holds the body of the function that I want to call for the finalizing the code. Thanks to the lambda syntax, is very close to in syntax to having a clean try finally. The only thing you have to add extra compared to a real language implementation is that you need to create an object, and second, that you need to call the functions upon that object. But other than that, Lambda allows you to have a very clean implementation. I'm indenting things here so it reads neatly and elegantly, very similar to try finally code. Now, there's a catch. You may recall what I said about the life of a function. Let me remind you. Not here. Hold on. I want to show you from what I was showing on the lifetime of an object, which is the next one. Hold on with me. Please wait with me for a second. Yeah, here. You need to keep in mind that RAII works by the lifetime of the object that you are encapsulating it with. Now, this is the yellow part of it. This is the function or code block that forces the lifetime of the object. So in order to make the try finally code block behave the way I want, I'm forcing a code block to force the lifetime of the object. That is why I have these two braces here. So I'm forcing the try finally object to live only here. Then it will be created here, but by having this nested code block, I'm forcing it to be destroyed at this point. The moment it gets destroyed, then I'm forcing that all this logic by the try body and the finally body get executed in sequence. Let me show you what happens by compiling this code. Hold on, not here. I'm in code. Let me change to project one. We're in project one right now. I compile this code. Okay, I go to the command line. I will call this code, which is project one. Okay, you see those 10 sentences of the try code block were executed, and right after that, the 5 sentences of the finally code block were executed, and then the program was terminated, end of the test program. So this is a normal run of the program. And you can see here on the source code that it executed exactly the way it's laid out here in the code, in the source code. Now let us introduce intentionally an exception is thrown inside the try code block. Then what happens? Let's compile this one again. Now we go back and execute this project. You see that the first 4 sentences of the try code block were executed. Then they get interrupted because the exception was thrown. Yet, you see that the finally code block was executed. All 5 sentences of the finally code block were executed. You don't see here end of program because this program didn't terminate correctly. Again, if you look carefully at the code, there's no try catch. there's no handler other than the main routine, and the main runtime library will simply yield an error on the command line, which is the error you see here, abnormal program termination. So this is intentional just to show you that because I didn't have any exception handler, it went all the way to the runtime library, and then the program had an abnormal program termination. But yet we had successfully the opportunity to run the finally code block to do whatever cleanup we need to do. So this is just showing you that this logic works. We have a fake or artificial implementation of a try finally code block for C++, which may come handy for some use cases like the one I just showed to you. Let's go now again to the object. For those of you that are curious, you will see that the implementation is really very straightforward. Again, I'm just using RAII in order to implement it. What happens is you need to call try, as I showed to you in the main code. When you call try, you pass the actual function that behaves as the try code, in this case by using lambdas. Then try will receive a lambda function and store it into a local member called try, and it will also set a flag. We need to set these flags because the whole object is designed to behave with both functions assigned. If you didn't assign either one of the functions, then the behavior is unexpected, is undefined. So there's a check here because there's two internal booleans that get set only when you actually define both codes, the try and the finally code, then the two booleans get set. When they finally get the point to be executed, those two booleans get checked. If for some reason either one is not defined or both, then it will throw an exception, flagging you, hey, you did something wrong. You are not assigning both together. Let's try to do that just by temporarily remarking this one out. So I didn't set finally, and because I didn't set finally, when this code is executed, let me go back here.
Is there any chance you could zoom the code in when you show the code a bit? A couple of people mentioning it's a bit tricky to read at the size it is. So just,
Sure.
Increase the font. Yeah.
Sure, no worries. We can do that. Actually, I thought this size was enough, but no worries. We can always increase it to make it.
It's Conrad. He's getting old.
No worries. I hope this one is better.
Perfect. Yes, thanks.
All right. So I just show you that I forgot intentionally to define finally. Then when executing it, I get an exception. So because I didn't have an exception handler, I don't see the actual message that I'm showing with the exception handler by saying, hey, try finally code block malformed. But if I had a try catch, then you would get this notification in the exception object. So just when you know that there's this like an internal guard, unfortunately, you don't have a compiler error because this is not a compiler feature. This is actually a runtime feature with RAII. So the only way I can flag you that you did something wrong is actually at runtime by raising an exception, throwing an exception. Okay, let's go back here and redefine this code. We re-implement it. Okay. So as I showed to you, this is working. Now you will say that this code is everything is defined internally. Okay, let's go back to the use case that I originally flagged to you as the one that calls or cries for having a try finally block. So that was the number 1. This was the number 2. Then we have the number 3. And the use case I showed you that was crying for a try finally block was this one, using of a database access. Then I will give an example of this use case. We go now to file number 2. I change the project to number 2. I have a very simple mock-up database. It's just to show you the behavior, but it applies completely by having real-life databases. So here, I'm accessing the database is created outside. This database is created here. I'm using RAII for the database itself, so I don't need to shut it up because it will be destroyed automatically by the compiler at the end of the program. And here in the try code, I'm appending and deleting some records. And then finally, I'm posting the data for those records. Now, if you are a master with Lambdas, then we need access to my database. One way would be to add database in the argument. Another way, which is the one I always prefer, is just use a generic referencing here, which means you can take any of my outside variables. So this way, by adding the generic reference argument here in the Lambda, then the Lambda truly behaves like a real try finally block. I don't need to add any specific variables here. I simply have access to anything that is visible at this point. When I start this code block, anything that is visible or has been created before this code point is immediately visible by my Lambda. Then by using this neat feature of Lambdas, again, I can truly mimic or replicate a try block by having full access to any variable that is already defined, doing something with them, assigning them, blah, blah, blah. Since they are called by reference, I can do anything. If it's a numeric value, I can assign a value, I can do whatever. I'm doing it on the real variable because they've been captured by reference by the Lambdas. So this is a pretty neat way to implement a try block and finally block exactly as they would be if they were implemented by the compiler. So let me show you what happens now. Same thing here with the finally. I'm using the catch by reference argument of the Lambdas. Then let me compile this one. Compile this code. Go here again. And now I call that one, but this is project 2. So this is a normal flow with no exceptions. So all the flow of try is executed, which is first the database is created. That was outside of the try finally block, but then within the try block, we append records, delete records, blah, blah, blah. And in the finally code, where is when you do the final cleanup or final action that you want to implement it, we do the data posting. So we're posting here the record finally. Then we get here you can see that the program finishes here when I put this line. And then after that, the main code terminates, the main function terminates, and then the compiler destroys any object that are at the highest scope level. In this case, my database. My database is at the main level code scope, then it gets destroyed at this moment. I did this intentionally on the destructor so you could have some visibility of what's happening, what's going on. So I did intentionally visibility when my database object was created. And also you get visibility when my database object is being destroyed. The destructor is being called. So everything so far so good. Let me again introduce some bad behaving things. Some exception is thrown inside the try code. Some appending of some records went bad, or a validation went bad, like the example I gave you on the presentation. Then let's compile this again. We execute this sample project again. And you see that not all records were appended, it's only some of them, but the finally portion was called. So we had a cleanup code of the database. We don't leave it into an unstable, undefined state. The data is posted, but the program had an abnormal termination because we were not handling the exception. So the program crashed, aborted, whatever you want to call it, but the database was cleanly finished up the way we wanted because we had the try finally code block. Now, as a convenience, the code is so simple that you don't need to actually compile. It's everything included in a header. So the only way, the way to use this simple try finally is just do this, include a header, try finally. That's number one. Number two is whenever you wanna do this try finally code block, open a temporary code block, a scoped code block. In this case is this. Optionally, I also like to do something like this, which is even more replicating what you will want to see on a try finally. Well, anyhow, you can accommodate things any way you want, but I think this is good enough to have visibility on what's going on. So after creating this in code block, scope it inside code block. That was number two. Number three is create an object of try finally class. You need to instantiate the object. That's number three. And then number four, call the try and finally methods of that object and pass as the argument your lambda function having your body of try and also the body of finally. And that's it. The rest is all automatically done by the object constructors, the object destructors, and RAII. It's so simple to do. As another convenience, I have the exact same header, but what I call it in debug mode. If you're just curious how things are happening inside, the only thing you need to do is, let me do that here. So in the sample program with the database, I'm going to remove the exception thrown here. And in include file, instead of the normal one, I'm gonna include the debug version. What will happen here is, for those that are curious, or if you really need it for some weird behaving and you don't know what's going on, then this may come handy for you. I do the compilation of this project again. Okay, we go back here. Look, this was the previous run with an exception, but I'm going back without having an exception. And then you get these additional commentaries from the try finally RAII object. So these are coming from the RAII object, and this may help you in case of a tricky bug that it's hard to catch. Then at least you know what's going on, and at least it's telling you exactly what's happening at the object level of the try catch object. Then going back here, I'll just add the exception so you can see. Let me just show you here one thing is, you see here that it's warning or telling us exactly when the try block has ended, and then when the finally code starts, and then when the finally code ends, and finally when the try finally RAII object is being destructed. Here you get this normal, means it followed the normal process flow. There was no exception thrown in the try code block, then it went the normal way, executed finally through the normal process. And then finally the destructor is reached through the normal path. When we have an exception thrown, which is the case I'm going to show you now, we compile this again. We execute this code again. You see again here, starts the try code block. There's a catch start, meaning there was an exception detected inside the try block. Then the try finally object jumps to the catch section. Then inside the catch section, it calls finally. Then you have the code of your finally code. Then it finishes finally, and then the object gets destroyed. But it's being destroyed through the alternate path. It had to handle the exception that was detected inside the try code block, in order to actually execute finally, the finally code block, and then throw again the exception. So this is the way we are emulating the try finally code block. We are simply intercepting the throwing of an exception to make sure that the finally code block is always executed. And then, since this is a try finally, this is not meant to handle the exception. So you need to rethrow it again. If you have a real try catch, that'll be on the next level, and that's apt to that try catch to do its own work. This try finally code block doesn't handle exceptions. It only makes sure that the finally code block gets executed. And then you have an abnormal code program termination, but you have the finally code block executed the way you wanted it to be. So this is the code, and I'm gonna share this with you in the repository. Bear with me for 1 or 2 days. I need to post it, and then I will make it available for all of you. And that's it for now. That's all I had to show to you in my presentation. I hope this helps. It's a very simple object, but as I have shown to you, there may be some use cases, corner use cases, where you may find this handy. And it's just a header file. You just need to include it and then use the convention I show, and you have a very, very handy try finally code block in C++.
Excellent. Well, thanks very much for that, Miguel. Let me just put you back on the Q&A. If you turn your camera on, I think we can put you on if you want to be on camera. It's up to you. It's your other source, I think, because I can see his source is down in there. Yeah.
Hold on.
I could be wrong. Yeah,
I'm
there's no
preparing
rush.
to launch the camera.
Woohoo! Like a rocket. Up to space.
Like a rocket. Yeah.
There you go. Excellent. Okay.
Thank you.
So let me do this. So we're side by side. There you go. Excellent. Okay. Thanks for that. It was a really good session. We had one about Delphi exceptions, and you actually explained, I think, quite clearly as well how exceptions, get nested in a way that made a lot more sense. You did make one comment that I just wanted to go back on again. You said that the try finally is a runtime function, or did I misunderstand? Implementation.
Yes, because normally you expect to be implemented by the compiler. Then the compiler introduces the low-level code to actually do the try catch. We don't have that in C++. So this is emulated by runtime execution with RAII, which is resource allocation is initialization. Actually, for your execution, there's no difference. The only difference is if you do a mistake, like I showed there, I needed somehow to flag the programmer if he forgot to define either try or finally. In case of the compiler, it tells you right away, you don't get a full compilation. But in this case, you get a full compile, but it's not good. It won't behave correctly. So to warn you that there's something's wrong, then I'm raising a real exception at runtime saying, hey, you forgot to define either try or finally, which doesn't make sense. You need to define both.
And what versions of the C++ standards support that, or is that something outside of the C++ standards?
This is outside of C++ standards. That's
right,
why
so
I made a replica.
Yeah, so this is only C++ builder?
Any C++, this is actually implemented in C++ builder, but any C++ will do. As I presented, C++ stands as the only major language today that doesn't have try finally implemented at the compiler level.
Yeah. Because that's what I was slightly confused about, because I'm not a C++ expert. I mean, I know how to code in C++, but I mainly have done C programs back in the day. I did all sorts of crazy C programs, even like an antivirus system back in the day, years ago, but in C. But C++, to me, there's always the bit that I think confuses new people are there's a C++, C11 standard, there's C17, there's C23, and so. And that's where, people say, well, there's generics, but it's only available in this version, and there's this, but it's only available in that version. But the try finally is something completely outside of that. It's a runtime thing. Is that what you're saying?
It's at the language level, not on the features, not on the runtime library. It's at the core language. Right. It's like if then else. It's at the language level. So try finally, like in Delphi, it's part of the language. It's a structure provided, a control flow provided by the compiler, the language. So in C++, as I explained, Bjorn Solstrup, the creator of C++, says no need. So they only implemented the exception handling. They only implemented the exception handling part, which is try catch.
Yeah, I like the way he says there's no. I like the way he says there's no need. That's Bjorn Solstrup, but really summed up. He's like, you don't need it. You'll be fine. Yeah.
Well, if you follow what I presented, he's right 90% of the time. That's what I intentionally presented, some use cases. The first 3 use cases are like, it's an immediate example of the most common use cases on, yes, you can use RAII for that. You don't need try finally. Use RAII, which is they are calling all the time for you to use. But there are some specific cases where you cannot use RAII because there's no allocation being deallocated, like that database example. I don't want to deallocate the database. I just wanted to do some cleanup on the database in case an exception is thrown inside the try finally call block. So those very specific corner cases, now you have a way to emulate or simulate the try finally call block.
Right, yeah, that makes sense. Well, it's not often you can say, well, Delphi does something at that level that's slightly better. That's almost like blasphemous for a C++ person to say that, but I'm glad.
well, this is one of them. Delphi has had try finally since it's Delphi. It was one of the key additions to the Delphi language when they put it together.
Yeah. I mean, I like C++. I think that most Delphi coders who experience enough can look at C++ code and understand what's going on, even if they don't take the time to learn C++. I have dozens of books behind me about C++, and they're all different. Every single one is covering a different subject. C++ is immensely powerful, but it also is one of those languages where I find it quite complicated, and I've been coding for a long time, but when you need it to do certain things, C++ is definitely, it's the proper surgical tool under some circumstances for doing things, and it's very interesting. Conrad, who's the guy that talked about not being able to see properly, he says, nice thing in Delphi, custom managed records can emulate RAII. Not sure if it's as efficient though. Yeah.
That I'm presenting tomorrow. I'm presenting that tomorrow.
Oh, are you?
The opposite thing.
That's right.
I'm presenting exactly the opposite thing is how to do RAII in Delphi with managed records. And that's a big feature because
I didn't even know that. That's funny. Well, there you go, Conrad. Miguel is ahead of you, of course. I'm sure he knew anyway. So your session tomorrow, are you doing your session live tomorrow? Is it pre-recorded? I'm not sure.
I'll try my best to send you the video in case I run into trouble. It's because I had last minute things with some projects here. So
you're a very good
I had the material.
Yeah, you're a very, very good live presenter anyway. You do it like that. And I think people would be amazed to know that it's completely live. It's, you're just getting on and showing the slides and coding and off you go. And it's really slick and well presented. So, I'm fine for whatever. If you want to do it live, that's good for me. You worry me because you're also very precise. I will be there at 1 and you're exactly there at a particular time. Because I was looking and thinking, he's not coming. but you turned up. Yeah.
I'm here. I'm here. I never miss one, Ian. I never miss one.
No, I know. We've been on plenty of sessions together in the past, and it's very good. Okay, well, we're going to call it a day there, I think. But thank you once again for your session. I look forward to the one in Delphi tomorrow. You speak multiple languages, human languages, and multiple computer languages as well. So you're a real developer's developer, I think. It's great, but I appreciate it, Miguel. Yeah. Okay.
Okay, all right. Thank you
Thanks
very
a lot.
much, and see you tomorrow.
Yep, see you tomorrow. Bye-bye.